Hi everyone, I'm Juniri from Gwangwon University, Republic of Korea. Today I will be presenting our paper titled Harassguard Detecting Harassment Behavior in Social Virtual Reality with Vision Language Models. This work addresses the growing problem of physical harassment in social VR platform and proposes vision-based detection system powered by Vision Language Model. Social VR platforms have experienced remarkable growth in recent years. VRChat, one of the most prominent platforms, recently surpassed 60,000 concurrent users. However, alongside this growth, online harassment has emerged as a serious and escalating concern. Unlike traditional social networking, social VR platforms provide immersive, embodied experience through personalized avatars. This heightened sense of presence makes incidents such as physical intrusion and sexual assault feel significantly more distressing to the victim. Indeed, the consequences are no longer purely virtual. Law enforcement agents have already investigated cases of virtual sexual assault targeting user avatars, and Interpol is actively developing programs for policing metaverse environment. This underscores the urgency of developing proactive, automated safety measures for social VR. Current social VR platforms do offer some built-in safety features. For example, Meta Horizon World introduces a personal boundary bubble features, and VRChat provides a configurable safety menu. However, these measures are fundamentally reactive in nature. They rely on victims to take action after harassment has already occurred. Furthermore, prior work has shown that users widely distrust this mechanism, citing a lack of transparency regarding how harassment reports are handled and what actions are ultimately taken. Platform developers have acknowledged these challenges, but are often constrained by limited technical resource and staffing. On the research side, the most closely related prior work is HardenVR, a deep learning-based harassment detection system that combines avatar hand position and controller input to achieve over 98% detection accuracy. While impressive, HardenVR has two critical limitations. First, it exhibits a high dependency on controller input. When detection relies solely on positional data, without controller input, accuracy drops to 0.6, suggesting that gesture-based harassment remains difficult to detect. Second, collection of fixed-off motion and head trajectory data raise serious privacy concerns. Prior work has demonstrated that such biometric data can function as a digital identifier, making it vulnerable to de-anonymization attacks. Our work is motivated precisely by need to overcome these limitations. Our contributions are twofold. First, we construct a vision-based harassment dataset, specifically designed for social VR environment. Second, we design and implement Harassguard, a vision language model-based detection system that relies exclusively on visual input. Harassguard not only classifies behavior, but also generates a natural language rationale for each detection, enhancing transparency and interpretability. To facilitate data collection, we developed a custom social VR platform using the Unity template, aligned with the environment of social VR platform. Avatar were equipped with upper body motion tracking via headset and controllers, and lower body movement was implemented using an inverse kinematic script to produce natural locomotion. The platform featured four distinct scenario rooms: communication, walk-a-pig, slingshot, and climbing room. Each room was instrumented with four third-person cameras providing omnidirectional coverage, along with a first-person camera for each participant. All video streams were recorded server-side for subsequent annotation. Based on the interpretation of prior survey findings, we've defined three categories of physical harassment. Aggressive behavior encompasses direct physical attacks, including punching, slapping, and striking with objects. Personal space violation covers proximity-based harassment, specifically rooming where an avatar's space is brought in comfortable close to another, and following stalking, which involves persistent pursuit over time. Disruptive behavior includes blocking, where an avatar obstructs another user's movement. All behaviors outside these categories are labeled benign behavior. Under IRB approval will include 14 participants ranging in age from 18 to 34 years. Participants performed both attacker and victim roles across all 4 rooms, enacting each category of harassment at least once. After validation and pre-processing, the final dataset consists of 3,408 video clips. Following each session, participants complete a post-experiment survey using a 5-point Likert scale. The user study yielded 2 noteworthy findings. First, perceived realism varied significantly across harassment categories. Looming received the highest realism rating, followed by blocking, stalking, and aggressive behavior. This suggests that behavior constraining a user's movement or vision are perceived as more realistic and threatening in immersive VR environment. Second, scenario context did not significantly attenuate the harassment experience. Mean unpleasantness scores were similar across the communication, wake pick, and slingshot rooms, with no statistically significant difference. This indicates that the inherent negativity of a harassing act persists regardless of the surrounding game context. HarassGuard operates as follows. Video streams from the social VR platform are segmented into clips, from which 6 frames are uniformly sampled. These frames, combined with a structured prompt, are fed into a fine-tuned VRM, which offers a classification label and region in JSON format. We investigated 4 prompt engineering strategies. The baseline prompt assigned the VRM role of the strict VR harassment classifier and enforced a structured JSON output. Context augmentation extends this by providing split definition of each harassment category. Few-shot prompting injects labeled example input directly into the prompt. Chain of thought prevents an older internal reasoning chain. We also decomposed the classification task into 2 stages. Stage 1 performed binary classification. Stage 2 performed fine-grained multi-class classification into aggressive, personal space violation, disruptive, or benign behavior. This composition reduces confusion arising from combining subtle harassment subclasses with benign behavior in a single classification step. Now turn to the experimental result. For stage 1, the baseline prompt achieved 66% accuracy. Context augmentation raised this to the 80%, and adding COT reasoning further improved to 81%, both representing substantial gain over the baseline. After fine-tuning on 200 video samples, performance improved consistently across all prompt settings. COT prompting achieved the highest accuracy, closely matching the transformer-based baseline, which was trained on over 1,000 samples. For stage 2, overall performance was lower, reflecting the increased difficulty of fine-grained behavioral distinction. Among fine-tuned variants, few-shot prompting achieved the best result. Interestingly, COT was less effective in stage 2, suggesting that direct exposure to labeled example is more helpful than structured reasoning. Taken together, these results demonstrate that HarassGuard achieved competitive performance while requiring significantly fewer training samples, underscoring its potential for data-efficient adaptation. Summarize, this paper makes 3 primary contributions. First, we construct a vision-based harassment dataset for social VR. Second, we propose HarassGuard, a VRM-based system that detects physical harassment using only visual input, enhanced through prompt engineering and fine-tuning. Our system achieves up to 88% accuracy in binary classification and 68% in multi-class classification, while offering interpretable, language-grounded detection rationales. Third, we demonstrate that HarassGuard achieved these results with substantially fewer training samples than conventional baseline, highlighting its suitability for low-resource settings. Looking ahead, we plan to evaluate HealthGuard with locally deployable VMs to reduce latency and enable real-time deployment. We also intend to extend the system to support diverse avatar types found on real-world platforms, and to fine-tune on the full dataset to further improve multi-class classification performance. Thank you very much for your attention. I welcome any questions.